모여갖고
디테일하게 좀
얘기 좀 하고
얘들한테 뭐를 하면
오늘 계약을 해야 돼.
So we are just missing the carbon balance, which is this big formula. So in fact it's a carbon balance, supposedly that the carbon is following the oxygen. That means we design the furnace with the, let's say, optimum oxygen consumption. That means here we have put enough cojets and enough lenses to achieve, for example, here it's a bit too big, but let's say we want to achieve 45 cubic meter oxygen. And the model is adapting the charged carbon to compensate the oxygen input, not over-oxidizing the slag.
Yes.
That means we want to keep 30% Fe, or even, let's say, 20% Fe. Okay? Then you see that the carbon has been adjusted here. It was 12, has been increased to 18. Okay, this is stupid figures, don't stick on it, but it's just to show that the program is adapting the carbon amount. Okay? So this is the philosophy. I put my oxygen tools, I run my process, and I see how much carbon I need to put. Another example, if I put here some pig iron, solid pig iron. This is a material containing already high carbon.
Yes.
So I don't have so much possibility. So I remove this and I put 20% pig iron.
Yes.
You see my material balance is unbalanced. So I balance it again. And you see I have decreased the carbon amount.
Yes.
Okay?
That means the carbon contents in the pig iron. Because of that, right?
Yeah. Because what I want is to have productivity of the furnace and good consumption figure. Okay?
Yes.
So I fixed the transformer rating, but as well the fossil energy. Fossil energy is driven by the oxygen.
Yes.
And if I put oxygen, in order to avoid to oxidize the iron, as I explained you yesterday, I need to put carbon. Okay?
Yes.
That's why in this calculation sheet, the carbon is depending on the oxygen. Alright? So, that means that I calculate the oxygen I have available, and I deduct from this oxygen what will be, let's say, absorbed by the other elements. And because I have a different behavior between melting and refining, I have two parts in the equation here. First of all, I have the oxygen for melting, minus the silicon I will have from the scrap, because the silicon will be the first to be, let's say, burned, and I assume it will be during melting. And dephosphorization as well will be done during melting. And then I have the oxygen during refining, from this part here to this part, minus what I will consume during refining by other elements. We will see later what it is. That means the mangan will be oxidized during refining, because then carbon is going down, so mangan is no more protected, and the resulting iron reduction oxidization will be done during refining either. Of course, I will oxidize some iron during melting, but it will be balanced and re-equilibrate during refining. Okay?
Yeah.
So, I mean, during melting, I don't care so much. Okay, let's see in detail what it is. C22 and D22. This is the volume of oxygen. Oops. You calculated here from the lens and from the cojets. Okay? I split them because I have different efficiency. You see, oxygen efficiency lens, oxygen efficiency cojets. Yeah? Oxygen efficiency L lens, oxygen efficiency cojet. And if you look where they are, cojets, oops, here. This is the two parameters here.
Yes.
Yeah? And each time you have a small comment when you click on the cell. Yeah?
Normally coded is much better than autobalance.
Yes. Okay. Sil is the silicon content in scrap, and you can see it's coming from this table. You remember from yesterday in the material balance. Yeah. This is the silicon, total silicon content from the scrap, or charge mix, let's say. Yeah?
Yes.
Okay. This value here is a gimmick. This is from here because I was faced once upon the time to a Japanese project, and this Japanese had special process injecting ferrosilicon or ferroaluminum, and as well another one was for stainless steel, where they were injecting ferrosilicon during, let's say, flat bath period to reduce the chromides of the slag.
Chrome.
Yeah, chromium oxide in the slag.
Stainless steel.
Yeah. So they were not using aluminum but ferrosilicon. So that's why I have these two, let's say, input cells where I can use this.
Additional
Yeah.
silicon.
But it happens to me only twice in my life. Yeah. Once aluminum injection in Japan, and once silicon injection for stainless steel. But I know that for POSCO stainless steel, the philosophy is to use a lot of oxygen, a lot, compared to others. Eh?
Yeah, that's right.
So it will be useful for you for your.
Yeah, that's right.
Yeah.
So it's in Korea and Japan's import from raw material from Australia and Brazil.
Yeah.
There are so many phosphorus and they have P phosphorus. Yeah. So and when we addressed our technical document in the EOSC as like the conference, and Korea and Japan is concentrated on how to do these phosphorizations. So and silicon and aluminum and the killed steels is very useful for us and to other steel making.
Yeah, I understand. So it's prepared already here. Yeah? So we are here. So this is the meaning of this U36, because this is as well silicon. Eh? Of course, it doesn't consider that's the silicon powder has a certain analysis. You put kilograms. you put kilograms of pure silicon, so you have to calculate yourself.
Yes.
Okay. 0.8 is the quantity of oxygen that requires per kilograms of silicon. P2O5, you have seen that this is as well in the natural balance. Here is P2O5, phosphorus, yeah? This one here.
Yes.
Oh,
Q.
what is the matter with this button again? Then here, plus E82, this is the oxygen from the air. This one here, during melting,
Yes.
because I consider that the oxygen is reacting with the scrap during melting. Yeah? And you will not find the oxygen reacting during refining, times the oxygen efficiency, which was 50%, as you remember. Okay? So, because it's flow rates here, you have to multiply by the melting time divided by 60 to have in hours and time tons. Okay?
Yes.
All right. So this is supposed to be, let's say, this is oxygen. This oxygen has to burn the carbon under certain ratio, yeah, of CO and CO2. So you have to as well compensate depending on the combustion, post-combustion.
Yes.
That's why you divide by 1 plus TCS. Yes, the TCS, this is the, in French, taux de combustion secondaire, which is the secondary combustion rate.
Tooth combustion rate.
Taux, rate is taux.
Taux.
T-A-U-X.
Taux.
Taux.
Now, how much is it? TCS1?
TCS1 is this one here. You see here. Alright? And this is TCS2. Or TCS melting, TCS refining.
Yes.
Right? So this was the part of the equation from the melting. Yeah? Where what is important to understand is that I have the oxygen from the lands, the oxygen from the air, minus the silicon which will be oxidized during melting, and the phosphorus which will be oxidized during melting as well. Right? Then comes the refining. So I have the oxygen from the lands and the oxygen from the cojet. And here I have the S36, which is the aluminum. S36 and U36. This one here. S36. This one. And U36. This one.
And I think to help us to understand more, and I think you explained in the whiteboard one more time, so to draw the EAF profiles and SLAM and explain that you have chemical reactions and oxygen flowing where, and as like the last day to help us to understand more.
Yeah.
Let's lift up the screen and draw the
But
that is better.
You like my sketch?
Yeah.
Okay. What I didn't mention is that you see 2 times the silicon injection, no, aluminum injection, because you see I may allow here some injection during melting, and I suppose that it would be the same for aluminum. So this aluminum injection is also injected during 5 minutes for melting, and the complete refining time. silicon and aluminum, in this case, will be injected during the complete refining time. Yeah? Then you have the mangan, oxidized mangan is, as you remember now, perfectly coming from this table. Okay? FeO as well.
Yes.
Yeah? And then you take into consideration the combustion rate of the refining phase. And then you convert this oxygen volume into carbon in kilograms. Okay? Times 2, because in oxygen you have 2 oxygen, O2, and then divided by the liters per kilograms and the per cubic, and then the grams. Okay, so this is the total carbon, and of course you have injected carbon, so you have to deduct the injected carbon, and you have to deduct the carbon in scrap. Carbon in scrap. Carbon in scrap. Where is it? C in scrap. Yes. This is this one.
Yes.
Huh? What?
I said some joke to him.
Okay. So divided by ton because it was in kilogram,
Yes.
plus what is remaining in the steel at the end of the heat. Yeah.
Remaining, yeah.
Okay. So this is pure carbon, and of course to calculate the coal, you have to divide it by the carbon content of the coal. Yeah, which is analysis H35, analysis H35. This is this one here. Yeah? Okay? Well, easy. You see, you are fresh in the morning. Yeah? So, the next stuff, but this is just for, let's say, indication. This is the carbon content at the end of the melting phase. So, more or less it's the same, let's say, logic. You have the carbon in scrap plus the charged carbon. Charged carbon is what we have calculated here, time the analysis, plus the carbon injected during the melting phase, minus the oxygen, the lands, the cojets. Of course, some of the oxygen will be used by the silicon, the phosphorus, yeah, and plus the oxygen from the air ingress, and again transferred into the, let's say, according to the combustion rate, and to convert this volume of oxygen into kilograms of carbon, yeah? And then you get this value. There is no particular, let's say, constraint on this carbon calculation. So that's why in certain case you may find here a negative value.
Negative value.
Yes. And what means the negative value? No, there is something wrong, but what is wrong?
Carbon is
Look,
too much.
Too less oxygen.
yes, I put 2 cojets. Boom. Huh? Of course, still, yeah? So I have not enough oxygen available. Yeah?
We need more.
And I have a little carbon powder, so I need to increase the oxygen.
같은 얘기네. 산소를 줄이든지 제가 늘리든지.
Oops.
전체 이해는 좀 됐는가?
Okay.
연철. 네. 이해됐어?
아직까지
거기서는
Yeah?
so I check the understanding status.
Yeah. Check first if he's asleep or not.
Yeah, that's right.
Because he's sick, so I mean, sometime when you have the flu.
예측 구체적으로 지켰다. 지금 I explained this small things to understand to him. Yeah?
Yeah.
일단 제 강의에서는 뭐 전기로든 일반 똑같은데 제 강의 가장 큰 게 이제 목표 온도를 맞추는 거고 이제 온도라는 거는 반응이 일어나는 부분이기 때문에 그 온도하고 연주 쪽에서 필요한 온도에 이제 목표 온도를 맞추는 거라 그다음에 성분을 조정하는 거라. 그래서 아까 뒤에 쭉 분석해 보면 카본, 설파, 뭐 피, 뭐 망간, 메레 5대 원소가 있거든. 그걸 가지고 지금 써놓은 것들도 다 그 원소거든. 근데 그 중에서도 이제 카본하고 산소하고의 이 반응에서 이제 대부분 반응이 일어나게 되는 그 자체가 망가도 마찬가지로 좀 오라고 붙잖아. 그래서 그 다음에 또 하나가 제가 해서 또 중요시 여기는 뭐냐면 슬라그 메이킹이라고 하거든요. 제가 슬래그 성분에 이제 P2O5나 AR2O3 아까 나오잖아, 그지? 그 다음에 FeO 그런 부분들이 이렇게 그 외에도 이제 시제가 다 들어있는데 대부분 핵심은 이제 거기에 들어있는 FE를 얼마나 그 용광수로 다시 보낼 거냐, 그거를 어떻게 평등한 상태로 만들 거냐라는 부분이 이제 가장 중요한 부분이지. 그게 많으면 실수율이 많아진다고. 그래서 지금 카본이 들어있는 양이 있고 또 목표 카본도 있다고. 목표 카본이 있으면 산소를 가지고 카본을 제거하게 되면 이제 CO 해서 나가게 되고 또 일부 산소가 너무 많이 불어가면 FE까지 뽑아서 슬라그 FE 성분이 많이 되겠지. 근데 그런 어떤 이큐블럼 상태를 어떻게 만들면서 목표하는 강을 만들어낼 거냐라는 부분에 이제 돼 있는데 지금 이제 카본하고 카본 양하고 그 산소 양하고 이제 비교를 한다. 그래서 넣은 양 빼기 들어간 양 빼기 넣은 들어간 양 빼기 나오는 양 뺏기는 양이 있으니까 그 수식을 좀 간단하게 써놓은 거거든요. 근데 그 내에는 이제 여러 가지 뭐 넣고 빼고 이제 사실은 저기에서 하나 좀 약간 빠진 게 뭐냐면 그 뭐 카본을 넣든 망간을 넣든 뭘 넣으면 100% 그게 반응을 또 안 한다고. 그래서 그게 수식에 되어 있는지 확인을 못 했는데 그거에 또 원단위가 되는 실수율이나 이게 또 있어. 이제 약간 그 설비를 드는데 그런 것까지 들어가면 이제 정확하게 계산이 되는데 그렇게 돼야 이제 메테를 발라서 그렇게 딱 생각을 합니다. 그래서 용광 평면을 경계로 해서 슬라그층과 용광 사이의 반응을 어떻게 조절해 줄 거며 그 목표 온도에서 거기에 들어있던 P2O5 P가 밑으로 용광소 들어오면 안 되잖아. 그러니까 이제 온도라든지 뭐 서로의 그 용광 성분과 슬라그 성분의 밸런스를 맞춰놔야 이 연주가 끝나더라도 그게 P라든지 그대로 남아있게 되는 거지. 그거를 하는데 사실 제강의 일이라고 되겠죠.
You should do it in English, huh? It's good training for everybody, then I can also understand what
It's
you
just
say.
a basic.
One thing you have as well to understand is the difference. What is the limit between melting and refining? It's arbitrary anyway. Yeah.
Arbitrary?
Yeah. It's let's say there is no scientific criteria to decide now it's melting, now it's refining. So this limit you have it here, which is 322 kilowatt hours per ton of steel, liquid. Yeah. Of course, here you have the scrap and the liquid iron. You don't have the DRI. DRI is fed only on flat bath, never.
Yeah, that's right.
Okay. But you are allowed to put DRI in the bucket. Here you have HBI or DRI in bucket. Yeah? And then in this case it will be considered in the material balance in there. Yeah? Because here in the analysis you have HBI in bucket here, which will be included in this column here. Alright? Okay. So then of course refining is the tons plus hot yield. And of course the 322 is the enthalpy of the liquid steel at 1530. So we consider here the overheating energy, yeah? And I mean this is difference of temperature, and above this temperature we consider that you need 0.236 kilowatt hour per ton and per degree C. All right?
And then
민주 3일은 뭐라고 이해했는지.
Okay.
1630도까지 톤당 1도씩 올리는 데 필요한
비율하는
엔탈피?
Because here, look,
뒤에다가
here,
질량만 높으면 되니까.
specific heat.
no. Here I consider that I have a yield and etc. Yeah. To be sure that I don't make a mistake on the liquid steel I will produce,
이렇게 됐으니.
and the liquid steel, because this supposed to be liquid steel. Okay? But this is a trick to be sure that you don't make any calculation mistake, because you may have a discrepancy between the yield you have calculated here and the real yield. I mean what you need to put in the furnace. So that's why I have this small equation here
Yes.
to be sure that you see here I have this mass, this weight, and I loop back again here with the same weight again, minus the liquid steel tons. It should be zero. It should be zero. Yeah? But to be sure, I add this again. Alright? So then the slag is something equivalent. So I have the scrap, and this is more, let's say true for the slag, because I've calculated here a slag amount here or here. Yeah. So I take this slag amount, okay, and I consider that I need 600 kilowatt hours per ton of slag. All right. So for refining, this is then I take the slag and the dust, and I need 0.05 kilowatt hour per ton of slag and degree C. Yeah. And I consider that the slag is 50 degrees warmer than the steel. I made several measurements, and it's in this range. Can be 70, yeah?
Yeah, it is only applied in the EAF and lead polishing. It's a BOF steel making is a different thing. BOF.
BOF is different, of course.
Different, yeah. It's
Because BOF, the agitation between the steel and the slag is tremendous first, and secondly, you don't have any arc in the BOF.
yeah, that's right.
So steel and slag have more or less the same temperature in the BOF,
Yeah,
not in the
yeah,
EAF.
because the slag temperature high, it means the EAF and lead furnace using the arc, and then the slag is a high.
In the ladle furnace, is not exactly the same, because ladle furnace, you have most of the time the slag, let's say colder than the steel. Why? Because you have a lot of air ingress, which is cooling down the slag on top. So the slag is warmer in the area of the arc, but outside is much colder.
Yeah. Okay.
So and then because the slag here, that's crazy, yeah? Excuse me. I don't. Stupid button. Okay. So this line is precisely calculated here. So again, as for the steel, yeah, I take what I am missing from the previous D39. This is this one. Yeah. So I consider the energy. I forgot to consider in the previous equation. Yeah. Okay, this one. All right. It's okay for all this stuff? In fact, I will summarize later again on the board. Then the losses. Okay, this is here. This is let's say the losses are time related. Because, so I have the melting time first, charging time, the baskets, then H56, this is the electrode slipping, or let's say adjustment,
Yes.
plus the delays here, and I consider the delays having 80% of the importance compared to the other waiting time, because the furnace is going to cool down.
Yes.
Yeah? And the delays are, let's say, having half the thermal losses compared to the melting time. So convert from minutes to hours, and then I consider all these energy losses. So 26 is the panels, roof, and gas. Okay. So this was the time-related losses. Now you have the ohm losses. It means you have current in the secondary bus bar, and if you have current, you have a resistance, so you lose energy there. Yeah? So this is the test to know whether you are in AC or DC. If you are in AC, you have 3 times the losses because you have 3 electrodes. If you have DC, you have just 1. So this is the short circuit resistance. Yeah? And then the current in DC, in AC, and the current in AC, square. Yeah? Because this is the ohm loss, ohm load. So this is resistance times current square, and then you have to consider the time. You remember the ohm loss, yeah? Resistance times current square times time. Huh? Okay, then I have the water, which is treated a little bit a special way here, because I consider that I have to evaporate the water and to dissociate a little bit. Yeah. So I have the evaporation energy here, and then to bring the steam at the from 100 degrees to the off-gas temperature. Yeah, this is the evaporation energy.
Yes, yes.
because water is liquid in scrap and then has to be put in the steam, and then from the steam to 100 degree to the off-gas temperature. The losses for refining, so same. So I have 80%, 80% of the delays during melting, and I have 20% of the delays during refining. Yeah. So measuring time, this is the temperature measurement, tapping, repair, and etc. So I have delays I count for melting, and delays I count for refining. So again, the energy losses from the panels and the roof, and the off-gas. G32, this is this one here. I am missing this one here. So I have to reintegrate this one in the losses, because this is supposed to be the radiation of the lower shell. And I forgot to integrate in the losses. Okay, doesn't matter. So, and then again the ohm losses in this case. But I don't have water to evaporate anymore. Water is gone for the melting phase. Huh?
Yes.
Okay, let's summarize again at the board.
I can shut down this. How about, Michelle, how about break time to have a coffee and then talk?
Okay.
Okay?